transition occurs at one place, and for odd values of n, it occurs somewhere else, or something, or there's some, or the location of the transition oscillates in some weird way. No one believes that this should happen, but this is sort of what's missing. And Freegutt's result is really based on the sort of abstract theory of analysis of Boolean functions and their sharp thresholds. And it's somehow too abstract to tell you anything about where the transition is occurring. And even comparing what's the location of the transition for one value of n and another. But it's still, as you'll see later on, a sort of very useful result to know. Okay. So one of the main things I want to do in this lecture is to describe the series of predictions coming from statistical mechanics, which describe different phase transitions these models undergo as we vary the density of constraints. Okay, so yeah, and each of these the models that I've mentioned are supposed to be in the same universality class, and essentially what that should mean is that qualitatively they have the same sort of transitions, so which I'll describe in a minute. But okay, so the origin of this work really goes back to work of a sort of famous physicist Parisi in the late 70s, and his work on what's called the Sharrington-Kirkpatrick model. So this is what's called a spin glass, and it's sort of a toy model for understanding the magnetic properties of certain alloys of metal, in a sense. So you can think of something like an alloy made of some fraction of copper and magnesium, and you'll have, and the way in which the particles sort of align in that piece of metal will be sort of random, and depending on how they're aligned, they'll have sort of different magnetic interactions with each other. So the Sharrington-Kirkpatrick model is sort of is a mean field version of that. It's a probability distribution over the hypercube plus, so each variable is either 1 or -1, and there's the weight is if you know what the Ising model is, it looks like that. There's a Hamiltonian, which is a sum of sigma I, sigma j, but there's also a random interaction on each of the pairs, and these are IID normal 0, 1s. And so sometimes that's positive, meaning that those two variables want to be the same. Sometimes it's negative, meaning that they want to be different, and those are chosen randomly. And so using like really wondrous and it's sort of hard to believe that they're true sort of ideas, Parisi was able to say sort of a great deal about this model. Gave the so-called Parisi formula for sort of the exponent that describes the normalizing constant here, and a lot about the way in which this measure splits up into, decomposes into clusters and so on. And nonetheless, but in the last 15 years, mathematicians have made tremendous progress on understanding these models. Work of Guerra and Talleyrand established the Parisi formula, and a few years ago in this conference, Panchenko talked about his work on ultrametricity for the Sharrington-Kirkpatrick model, which is sort of a description of the way of clustering. Now this is a dense model because every variable interacts directly with every other variable. Whereas the constraint satisfaction problems we're thinking about are very sparse. It's like the average degree of the graph is just a constant. Or in the random k-sat model, each variable is in just a constant number of clauses. But even as early as the mid-'80s, Mézard and Parisi sort of understood that the same sort of ideas that were applied to these spin glass models should also apply to sparse random constraint satisfaction problems. A very complete description of their behavior was given more recently, maybe a bit over 10 years ago, by a collection of physicists, and for what you can call the one-step replica symmetry breaking universality class of models. And I'll say on the next slide what I mean by those words, because at the moment that's just sort of random jargon. Okay, but the point is that all of these models should undergo the same sort of set of transitions, and you should be able to predict where they are for each of the models. Okay, so what do we mean by when we're saying replica symmetry breaking? Replicas just really means samples from the distribution. So it's like you have your random set of constraints, and so there's some collection of solutions to that set of constraints. And then a replica just means picking uniformly from that distribution. So random colorings of a graph. And so you can ask, if you pick a few random colorings of a graph, say, how do they look with respect to each other? And so there's, well, so in at least in the models we're talking about, there'll be really two possibilities. In general, it could be more complicated than this. So the simpler case is if they're replica symmetric. So imagine you take two replicas, so just randomly chosen colorings from your graph, and you could look at the Hamming distance between them, just the number of vertices in which they have the same or different numbers of colors. In the replica symmetric regime, this is supposed to be concentrated. So it's like saying you pick some colorings. All of them will be sort of the same distance from each other. In the one-step replica symmetry breaking regime, and you look at the distances properly normalized, then the distances will be concentrated on two possible values, basically corresponding to either having solutions that are close by to each other or distant. And both of those will happen with a constant probability. And this is essentially a phenomena of clustering. When the model is replica symmetric, there's either no clustering or the clusters are small. But when you have one-step replica symmetry breaking, you have the solutions break into clusters, and they're dominated by a few large clusters. Okay, but there's no extra structure beyond that. You have solutions breaking into clusters, but you don't have sort of clusters of clusters or clusters of clusters of clusters, which does happen in more complicated models. In the Sharrington-Kirkpatrick model, for instance, there's sort of an infinite hierarchy of clustering in the measure. Okay. And the final thing is, if you look at sort of variables within the solution, you could ask, sort of randomly picked, you could ask, are the values of them correlated with each other? And in the replica symmetric case, they'll be essentially uncorrelated. In the one-step replica case, they'll be correlated. Okay. So let me sort of describe this now in pictures in this sort of ink blot-looking diagram. What this is meant to represent is is the space of solutions and the way in which that sort of splits up into clusters. So you could imagine, okay, so what is a cluster of solutions? You could talk about two solutions to a problem being adjacent if they just differ in one variable, or maybe a small number of variables. So if you can define a notion of which solutions are adjacent, you can talk about the connected components of those solutions. And so the clusters will just be the connected components in that graph. Okay. And then the transition is, as the density of constraints increases, the way in which the solutions divide into clusters changes. So at the lowest density of constraints, all of the solutions will, or either all or almost all of the solutions will just be in one giant cluster. This is sort of the easy case. This is also if you're interested in the algorithmic question, this is the easy regime. There are algorithms that will efficiently find solutions sort of throughout this regime, maybe at least almost up to the threshold here. And in principle, you'd imagine that they should work all the way up to the threshold. So you can, so this is sort of easy algorithmically and no clustering, or almost no clustering. Then there's a transition, and the space of solutions sort of shatters into exponentially many clusters, each with an exponentially small fraction of the total number of solutions. So these clusters are very small. Now you have clustering, but it's still in what's called the replica symmetric regime. And the reason for that is if you say you pick two solutions, then you're almost always going to pick two that are in different clusters. So the fact that it's clustered won't sort of show up if you look at a smallish number of just samples from the distribution. They'll all look the same distance away from each other. Much closer to the satisfiability threshold, there's another transition, the condensation transition. And in the condensation regime which follows, you still have clusters of solutions, still have exponentially many of them, but the biggest ones have most of the solutions. So the largest one will typically have a constant fraction of the number of solutions, and if you look at the million biggest clusters, they'll have typically have 99% of the solutions. A more refined prediction is that if you look at the relative cluster sizes, they'll follow a probability distribution that's called a Poisson-Dirichlet distribution. So this is now where it's replica symmetric, and basically it just boils down to the fact that if I pick two solutions at random, there's some chance that they'll both be in the biggest cluster, like a positive probability, and then they'll look close to each other. But there's also a positive probability that one will be in the biggest cluster and the other will be in the second biggest cluster, and then they'll look far apart from each other. Okay. The final transition is then the satisfiability threshold, after which you have no more solutions and, of course, no more clusters of solutions anymore. So all of, this picture all looks kind of a bit vague. I gave you a definition of what the clusters were, but there's really a lot more in the physics predictions than just these pictures. For each of the models, they have predictions of where each of these transitions occur as the solution to some equation. and they can tell you lots of things about what happens inside of each of these regimes. So what does a typical solution look like? How many solutions you have? For instance, they predict that if you look at the exponent of the number of solutions you have, it will look sort of analytic throughout the replica symmetric phase, but then have a phase transition at the condensation transition. And there's formulas for everything, but still only a few parts of this have been made rigorous. So, and we're sort of working a way to try and establish more of these predictions. So, so one of them, which is a joint work with Zhan Ding and Nike Sun, was in the random KSAT model, establishing the location of this satisfiability threshold at the point that was predicted by the one-step replica symmetry breaking prediction. Okay, so in the next lecture, I'll tell you more about how to actually compute what these thresholds are. But the next thing I want to discuss is just a couple of tools to understanding these problems and these distributions. Okay, so I'm gonna start off with the random coloring model, which is actually the one in which we can prove the least about, but it's probably, I think, colorings is probably something that more of you are familiar with. So and it's sort of easy to describe the sort of simplest sort of calculations you can do with these, and so, you know, what would be the first thing you do in trying to understand whether or not you can color this random graph with Q colors? The simplest thing to do would be to just work out the expected number of valid colorings that you have of the graph. So let Zn be the number of colorings with Q colors. It's going to grow exponentially with n, so we'll be interested in the exponential growth rate of the quantity. And so we'd like to calculate this, and you know, when it's greater than 0 will be sort of when we actually see colorings. And so if we to get an upper bound on the exponent, we could calculate the first moment, use Markov's inequality, and get an upper bound. Which is basically just saying if the expected number of colorings that you see is, you know, much smaller than 1, then the probability of having a coloring will be very small. And for to get a lower bound, the simplest thing you can do is look at the second moment, which is the probability that the number of colorings is positive. Well, okay, this is the you know, equation that's true for any non-negative random variable. The probability that it's greater than 0 is bounded below by the ratio of the first moment squared divided by the second moment. So if we can show that these are the same, or at least comparable, that would give us a lower bound on the probability of seeing some colorings. Okay, and it turns out computing moments is not too bad. But there's one thing that you need to do, which is first condition on the number of edges in your random graph. If you don't do that, you get a very, very bad results, or sort of, you know, fairly useless bounds. So, you know, the number of edges in the random graph will be binomial. So it will be very concentrated around its mean, which is about dn over 2. And so we'll condition on there being, say, m equals dn over 2 edges. And then how do you work out the expected number of colorings? Well, you could just first assign colors to each of the vertices before you've looked at which edges are in the graph. And then say, what's the probability that for that particular assignment of colors that it will be a valid coloring? In other words, what's the probability that none of the edges join two vertices that you assign the same color to? And so by symmetry, all that will really matter is how many vertices you have of each color, how many blues and reds and greens you have. So let Ci be the fraction of color I. And so there's a multinomial coefficient for the number of ways of assigning colors to vertices. And then this is the probability that it's actually a valid coloring. You don't add, none of the M edges join up vertices of the same color. And so if you apply Stirling's formula, you can write it sort of in terms of an entropy. But actually, what sort of fraction of colorings will give you or colors will give you the most likely, make it most likely for it to be a coloring? It's just having the uniform distribution, so equal numbers of each of the colors. And so it's maximized when all the Ci are 1 over Q. And so this is the formula you get for the exponential growth rate. If we didn't first condition on the number of edges, we would have gotten a different result, something that you can check that this one is bigger than this one. And so the reason for that is, okay, graphs with fewer edges have more colorings. That's, the more, if you put fewer constraints on the graph, then it will be easier to color. There'll be more colorings. There'll be a lot more colorings, actually. It turns out that if you don't do the conditioning, the expected number of colorings is dominated by very unlikely graphs that have much fewer number of edges than you'd expect from the binomial distribution. But because those graphs have just so many more colorings than a typical graph, they'll dominate the expected value. So very rare graphs will make a sort of outsized contribution to the expected value. And that's not what we want. We want to know what the behavior of a typical graph is like. So, and you can do this by first conditioning on how many edges you want to see. This effect of sort of very rare graphs or rare constraint satisfaction problems having sort of the biggest contribution to the expected value is a persistent problem in this area. And I think maybe a big fraction of what the work we try and do is to sort of tame the effect of sort of unusual graphs that sort of lead to huge contributions to the expected value. And so that's a very technical area, and therefore I'm not going to say any more about that for the rest of the lectures. But that's behind a lot of this. So okay, so you know this. So you could use this exponent, the point at which it's 0, then by Markov's inequality just gives you an upper bound on when the random graph is colorable with high probability. If beyond D1, the root of this equation, the expected number of colorings will tend to 0, so the probability that it's colorable will tend to 0. So this is an upper bound on the colorability threshold, but it's not the right bound. It's an overestimate. The reason for that is, okay, well, there are multiple reasons for that, actually. But the simplest reason for that is if you have one coloring, you'll always have many other colorings as well. And the simplest way to see that is just that there's a positive fraction of vertices of degree 0 in these random graphs. So the degree distribution of the graph will be a Poisson distribution. So an epsilon fraction of the vertices will be degree 0. So and a vertex that has no edges, you can make that whatever color you want in any of the colorings. So if you have one coloring, you always have at least q to the epsilon n colorings as well. If you plug that fact into Markov's inequality, that would give you a slightly better upper bound here. It would still be the wrong upper bound, but it shows you that this is also the wrong upper bound. You have to do more than that, but I also make this point because it emphasizes the fact that you have clustering of the solutions. Whenever you have one, you have a lot of nearby solutions as well. And it's not just a problem for the sort of isolated vertices or the vertices that are not in the giant component of the graph. Even within the giant component of the graph, there's still many local perturbations of the coloring you'll be able to do. Okay, so clustering, understanding the clustering of colorings and solutions to CSPs in general will be sort of a crucial topic, and sort of expressing that will be one of the main things I want to get across in these talks. Okay, so that was the first moment. What about the second moment? Working out the expected value of z squared is like counting numbers of pairs of colorings of the graph, which is like assigning pairs of colors to each of the vertices. So we could write Cij for the number of vertices that get color I in the first one, and then color j for the second color. And you could go through the same calculation, but now it looks like a more complicated formula, and it's not as easy to optimize. In fact, it's no longer in general unimodal. So there can be, we'd like it to be maximized in just the very uniform case where the fraction of vertices with color I in one copy and j in the other will be 1 over q squared for all of them. If that were the case, then if you do some more computations, essentially this formula would factorize, and the second moment would be the same as the first moment squared. You could apply the second moment method and show that, yes, you will have at least a positive probability of having a coloring in the graph. Okay, so now the space of all essentially stochastic or matrices or Cij's that add up to a positive and add up to 1 is a pretty big space, but we could parameterize it by a sort of simpler family, which is these are some, Cij is some q by q matrix, and we'll just have one value on the diagonal and another value off the diagonal. So when t equals 1, it's just all of the terms would be 1 over q squared. So if you plot this, log of this for a particular choice of Cij, in this parameterized family we looked at, you see that there's two maximizers. The first one up here corresponds to t equals 1. And so this is, by the way, this is the plot for 30 colors and average degree 198. Okay, so, and you can show that the maximizer occurs at t equals 1, which corresponds to counting pairs of colorings that look basically independent with respect to each other. The second moment will be the same as the first moment squared, and the second moment method will work. So this is everything that you want to happen. What if we go to d equals 199? There's still two maximizers, but here, the second one over here is bigger than the case of t equals 1. So this is t equals 28.8. What does that mean? It's pairs of colorings where where the two pairs look basically identical to each other. On most vertices, they have the same color. On a few, they have different ones. So this is another manifestation of clustering. It's saying that we're getting too big a contribution from pairs of colorings that are in the same cluster, and that's actually dominating the second moment, and will make the second moment method fail. So when you get close enough to the satisfiability or the colorability threshold, the second moment calculation will stop working. Okay, so just to tell you what is known for the coloring case. So what I presented here was essentially work that goes back to Akliopoulos and Noor in 2005, and they were able to show enough about do this second moment method sort of well enough to say for each D that the chromatic number, the minimum number of colors you need to color the graph, is on one of two values. And they did that by establishing this, not all the way up to D1, but fairly close. And I should say, this ratio, by the way, if it were converging to 1, then that would say that the probability of having a coloring would be tending to 1. But actually, you'll find that it converges to some constant like a constant, but not 1. So all that will tell you is that you have some positive probability of having a coloring that's sort of bounded away from 0 as n tends to infinity. But you can combine this with Freegutt's result for a sharp threshold, which says that if you know for some value of D that you have like a 2% probability of having a coloring, if you take a slightly smaller value of D, the probability will be at least 99%, as n tends to infinity. The fact that when you have a sharp threshold, if you know something with positive probability, if you move away from the threshold a little bit, then you can get that with probability tending to 1. So just to summarize, for colorability, the first moment we know that it's not colorable above some threshold and D. And the second moment method works up to some D2 that's strictly less than D1. And in between, it's still an open problem. So in the case of coloring, there's a prediction from physics, but that's still an open question. Okay. So that's, and so a lot of the work in establishing thresholds is really based around computing moments using the second moment method, but in more sophisticated ways than this. Okay. And so now I want to mention a second tool, which is called the interpolation method. This is an idea that comes from spin glasses. It was a beautiful invention of Guerra, and it was quickly applied to sparse random CSPs by Franz Leone and Panchenko-Talleyrand. And the formulation I'll talk about was developed by Arti, Germanic, and Tatali. And basically, the idea will be that we're going to start off with one graph and do an interpolate between that and having two graphs. So essentially splitting one graph into two in a smooth way in order to compare properties of graphs of different sizes. And the one I'm going to focus on is looking at the size of the largest independent set of a random graph. Okay. And to do this, a convenient way of parameterizing this is in terms of the stochastic block model, which is actually more commonly talked about by statisticians. It's like a model that they use for random graphs with some sort of community structure in it. You imagine sort of Democrats and Republicans here. And you have sort of a higher density of edges within the two groups than between. So in general, it will be a random, so in this case, we'll say a random graph with two sets of vertices of size n over 2, v plus and v minus, and density a over n edges within the two groups, and b over n density of edges between them. Okay, and we'll take a parameterization of these models. So GT will have these parameters, and what it's saying is when t equals 0, a equals b will be d, and you'll just get the basic Erdős-Renyi graph, though you won't see any structure, community structure. But when t equals 1, you'll have no edges between them and just two completely disconnected graphs. And there'll just be two copies of an Erdős-Renyi random graph, but of half the size. And the idea will be, as we interpolate, how does the expected size of the maximal independent set change? Okay, so I'll let AN be, so the density of, so the maximal, the expected density of the maximal independent set. So calligraphic I will be the size of the largest independent set. We take the expected value, then divide by n. Okay. So suppose you have a graph and you add one extra edge to it. How does that change the largest, the maximal independent set of that graph? Does it, I mean, obviously it can either stay the same or decrease. So when does it stay the same and when does it decrease? Well, there could be more than one maximal independent set. So the answer is, if you look at all of the vertices that are in every maximal independent set of the graph. So call this S of G. So the set of vertices that are in all the maximal independent sets of G. If you add a new edge in and you connect up two vertices in S of G, then the size of the maximal independent set must decrease because none of the maximal independent sets would be an independent set anymore. On the other hand, if you add in an edge, but it's one of the endpoints is not in every maximal independent set, then for that independent set, when you add in the edge, it remains an independent set, and so the size of the maximal independent set won't change. So really when we think of what happens when we add in an extra edge, it's a question of are you connecting up vertices that are in every maximal independent set in the graph? Okay. So now suppose we take the stochastic block model and differentiate in the parameters. So differentiating in B is sort of increasing the density of edges between the two halves of the graph. And you can think of that as sort of like some infinitesimal rate of adding in an edge between the two halves of the graph. And so the derivative of the expected size of the maximal independent set will just be based on what's the probability that this new edge connects up two vertices that are both in S of G in every maximal independent set. And so you can just write down the formula for that. Okay, and similarly, if we differentiate in A, now we're only adding edges within the two halves rather than between them. And so rather than between the V plus and V minus, it's either two vertices in V plus or two vertices in V minus. Okay, and then we could work out the derivative of our interpolation between these models. And so it will just be what the second one minus the first one divided by 2. And what you get is a minus a square of a random variable plus some other term. This one will be sort of small order, so we can kind of ignore it. And a square of a random variable is always positive. So essentially, the derivative will be negative up to some small error term. So the expected value at the end will be less than or equal to the expected value at the beginning. And now you should remember what the beginning and the end were. The beginning was one Erdős-Renyi random graph on n vertices, and the end was two Erdős-Renyi random graphs on n over 2 vertices. And so we've been able to relate the expected size of the maximal independent sets on these graphs of different sizes. And essentially what you get is a superadditivity. So an will be at least as big as an over 2 minus some small order term. And so by some, if you superadditivity argument, you can show that an has to converge. You might want to break it into blocks of slightly different sizes for this argument. You can do that too. Okay. Yeah, and so altogether, the argument will say that the expected size of the maximal independent set converges as n tends to infinity. And this is, and so this is one of the very powerful methods in, so this is the sort of simplest example of this very powerful interpolation method. And so I should end this half of the lectures here. Yeah. What is the value in them? So there's a formula that you could write down, and trying to. I should have put it in the notes for the lecture, so I could say you can look at it in the notes. It involves, so you first solve a measure-valued recursion, and then plug that into a functional, and then find the root of that functional. And that's the answer. So in the, so it's analogous to the, so I have the formula for random k-sat, which is, so you solve a recursion that looks like this, and then plug it into this formula. So the solution, so you were solving this equation for nu, then you plug nu into this, and look at the point at which this is equal to 0. And so it's an analog of that. Okay.